Welcome to the second part of our webinar series, Belt Drives and Accessories. In the first session, we covered the basics. Today, we'll dive a bit deeper into the technical details. We'll look at how V-belts and timing belts are constructed, what different types exist, and what to consider when using them. We'll also talk about key topics like tolerances, match sets, and international standards. By the end of this session, you'll understand what really matters when selecting and evaluating belts. Here's what we'll cover today. We'll start with the internal structure of a V-belt and explain how the individual layers work together. Next, we'll take a look at different belt types, from traditional wrap V-belts to modern timing belts. We'll discuss dimensional tolerances and why matched lengths are so important when several belts run in parallel. Finally, we'll talk about the relevant standards that ensure interchangeability and quality. We'll end, as always, with a quick preview of the upcoming webinar in this series. Let's get started. At first glance, a V-belt looks quite simple, but there's a lot of engineering inside. It consists of several layers that work together to provide flexibility, stability, and reliable power transmission. The load-bearing element is the tension cord, usually made from polyester or aramid fibers, which absorbs the tensile forces during operation. The load-bearing element is the tension cord, usually made from polyester or aramid fibers, which absorbs the tensile forces during operation. Rubber or elastomer compounds embed the tension cord, distributing the forces evenly and keeping the belt flexible. The outer fabric cover protects the belt from wear, oil, and dirt. This combination of materials ensures that a V-belt performs reliably under high loads and offers a long service life. V-belts come in different designs. The classic version is the wrapped V-belt, featuring a textile outer layer that makes it durable and ensures smooth operation. You'll find these in many standard applications, for example in machine tools or conveyor systems. Then there are raw edge or notched V-belts. Their inner surface has fine teeth that improve bending flexibility and reduce heat buildup. This allows the use of smaller pulley diameters. You can recognize notched V-belts by the X in their designation. For example, XPZ or XPA. They cost a bit more, but deliver higher power density and better efficiency. Timing belts work quite differently from V-belts. Instead of relying on friction, they transmit power through positive engagement. The teeth on the inside of the belt mesh precisely with the grooves of the pulley, meaning there's no slippage and movements are transferred exactly. The basic structure is similar. A tension cord made of glass fiber, steel, or aramid provides strength, while the tooth body is made from a durable elastomer. A protective fabric layer shields the tooth surfaces from wear. The exact tooth design depends on the application. Timing belts run quietly, require little maintenance, and need no lubrication. They're used wherever precise synchronization is crucial, such as in engine timing systems, machine tools, and robotics. Every belt has manufacturing tolerances. That's true for both V-belts and timing belts. Unlike rolling bearings, where tolerances are measured in micrometers, belt tolerances are specified in millimeters. For V-belts, this mainly affects the length. Two belts from the same manufacturer can differ slightly. For example, a 400 millimeter belt may have a length tolerance of plus or minus 5 millimeters. When multiple belts run on the same drive, they need to be as close in length as possible so the load is evenly shared. This property is called match length. If the belts vary too much, some will run under higher tension, wear out faster, and reduce the service life of the whole set. That's why manufacturers offer match sets with very small length variations, typically plus or minus 2 millimeters for short belts, and up to plus or minus 12 millimeters for long ones. For timing belts, tooth pitch tolerances also play a key role. These define how precisely the teeth are spaced along the belt. Even tiny deviations can prevent the belt from meshing perfectly with the pulley, especially in precision drives. That's why timing belts are manufactured to extremely tight tolerances, ensuring smooth, uniform power transmission and quiet operation. This is especially important for CNC drives, packaging machinery, and other applications where accuracy is critical. For belts to perform reliably, they need to comply with the correct standards. Both V-belts and timing belts are standardized to ensure that belts and pulleys from different manufacturers are compatible. For V-belts, common European standards include DIN 2215 for classical types and DIN 7753 or ISO 4184 for narrow section belts. In the US, you'll often find RMA standards such as 3V, 5V, or 8V. For timing belts, standards like DIN ISO 5, 296, or ISO 13050 apply. These define the tooth shape, pitch, and material properties. In the next webinar, we'll take another step forward. We'll explain the different designation systems for V-belts and show you how to calculate the correct belt length. You'll gain practical knowledge that helps you select and apply belts more effectively. We look forward to having you with us again. Thank you for your attention.